then let's get started. This talk is going to be about how the FVM works. The FVM is the virtual machine that we use on Filecoin for running our smart contracts, and also for running all of the state management logic that happens on chain. So we have a lot of really complicated smart contracts because they have to keep track of all of the pieces of data that's stored in the system called sectors, and make sure that they're being correctly proven, and to store for the correct amount of time, and the storage providers that are failing to correctly store the data are getting fined, all this kind of stuff. And this is actually, it's pretty complicated. The logic is very, very complicated. So this is why we have the FVM. When users actually deploy a smart contract system, at the moment they deploy it to an EVM instance that we're running inside of the FVM. So they can't currently deploy contracts directly to the underlying FVM, but we'll talk about that a bit later. Okay, so what is the FVM? First of all, I need to go through some terminology. Otherwise, we're all going to be very lost. The FVM is, again, Filecoin virtual machine. It's the virtual machine that we run the Filecoin smart contracts on top of. FVM is another tool, or another term you might hear. This means EVM on the FVM. So this is how we implemented support for EVM smart contracts inside the FVM. We literally built an EVM interpreter in Rust and then compiled this to WebAssembly, and then we run that as basically another smart contract inside of the FVM. Actor. So actually in Filecoin, we don't call them smart contracts. We actually call them actors based on the actor model. So we talk about how you run actors that can send messages to each other rather than saying smart contracts call each other. It's just slightly different terminology. Account is the same as an Ethereum. It's a top-level message sender. It is a type of actor. We consider every unit or every addressable thing on the Filecoin network is an actor. Accounts are a type of actor. Accounts do not run code. Well, sorry, they don't usually run code. They can actually run some code, but usually you send from your private key, and that they're responsible for letting you send messages from off-chain. IPLD. So how many people here have used IPFS? Okay, so you've all used IPLD. IPLD is what IPFS is built on top of. It's the underlying interplanetary linked data system. I know it's a mouthful, but it's basically an abstraction over different Merkle linked data systems or hash linked data systems. So it lets you instead of just using a raw hash to point to some blob of data, this is how most content addressing works. We take that raw hash and then we add a few bytes more to tell you the type of hash it is. Say it's SHA-256 hash or a Blake2B hash or whatever. Then we add another few bytes there to tell you the type of data you're pointing to. So it tells you this is Seaborn coded data, or this is a protobuf, or this is a JSON object, stuff like that. What this means is that when you give someone a CID, they can know how to interpret the data. Well, first they can know how to interpret the CID. They should know what data to expect. They should know if the data should be hashed with SHA-256 or Blake2B, and then they can also know how to then decode the data into structured data. This is actually when we talk about IPL, we talk about Merkle-linked structured data. Yes. Got it. So yeah, CID is a content identifier. Yeah, so that's what it means. But really, you can think of it as kind of it's a hash with some additional metadata attached to it. That's really all it is. And they're used on Ethereum as well. For I think ENS uses them in some cases for referring to content, because it's a very convenient way to refer to content without in an extensible manner, because you can just sort of keep on adding new content types basically. Okay, the next piece of technology used here is called WebAssembly. I assume that people are a little more familiar with this. WebAssembly is it's a new VM and assembly spec, actually primarily designed for web browsers, but it's really, really nice for a lot of reasons that I will talk about in a bit. It's a wonderful design, and it's just perfect for blockchains. Next, a message. This goes back to talking about actor models, where in an actor model, one actor sends a message to another actor. In our case, we actually send a message on a method. This is, if you've ever read about Smalltalk, it's the same concept where you have your objects or your actors, they can then send messages to each other on specific methods. We represent these methods by method numbers. If you're familiar with Solidity, Solidity has function selectors, but function selectors are kind of built in, where when you send or when you call another smart contract and Solidity, it sort of encodes all your parameters along with function selectors, one big binary blob. We break these out. So we have a method, or like the method number as a separate number that we specify, and then have the byte parameters as a separate thing. We do this because it makes it easier to sort of reason about like what functionality you might invoke without having to sort of parse the arbitrary data. So like if you're using Ethereum, like everybody uses function selectors, but technically you don't need to use function selectors. Technically you could just pass arbitrary bytes. We make this a bit simpler in Filecoin by saying, no, everybody uses method numbers. That's it. Okay. Chain message. A chain message is just a message, but it's like one we say is included in the chain. It's a top-level message sent by an account. The reason I make a distinction between a message and a chain message is like basically from your account or your local wallet, you'll send a message on chain. We'll then refer to it as a chain message. This is actually directly referenced by the chain. But then like when you're running an actor and your actor calls another actor, and that was not good, and your actor calls another actor, that will send a message from your actor to another actor, but that doesn't appear on chain. It's an internal message. You get the same thing in Ethereum. They're usually called internal calls. Yes. We use the method number. So we yeah. Yes.
We do not use function selectors on FVM.
No, but the method numbers are effectively equivalent. Where like we have a different way of deriving method numbers than Ethereum does for function selectors, but they're used for the same purpose. Where the method number tells you like basically it's like a port or an endpoint. You're sending. Yeah, that's what it's for. So like you just like invoke method 5 or something like that. Yeah. Okay. So now that I've covered some of the terminology, I had to get that out of the way. I know I said that the first part was going to be easy. I lied. I'm sorry. We have to cover the terminology, otherwise we can't speak about this. Now we can talk a little bit about why IPLD is so cool for building blockchains and for blockchain VMs. So as I said before, like IPLD is this abstraction of like Merkle-linked data structures or hash-linked data structures. And one of the cool things here is like hash-linked data structures are copy and write. So the reference to like the top level of the hash-linked data structure is a hash. And that means like if I want to modify some hash-linked data structure with many pieces in it, I can change the pieces that I touch, but I don't have to touch any of the other pieces. They can all stay the same. I build up a new Merkle tree and I get my new root, and then I can only store that new root. I don't have to like rewrite everything. But one of the other cool things I can do here is like if I have two smart contracts, or in our case, two actors, I can send an entire Merkle tree from one actor to the other actor without having to copy a bunch of data. So in Ethereum, if you want to call another actor or another smart contract, you have to like put all of your parameters in one big byte buffer and then send that all along, and that can be expensive, especially if the other smart contract doesn't actually care about everything you're telling it. They only want some piece. In the FVM, for a very low cost, you can send like an entire tree of data to someone else, because you just have to send the reference to the root, and that's it. So basically, it lets you have pointers in a system that usually wouldn't be able to have pointers. Another thing is, well, so I guess that's what I was talking about here. This supports pass by reference between actors, unlike in Ethereum where everything is basically passed by value. You can only pass objects by value. There's also you have user specified data layouts. So at Ethereum, like the Merkle tree is pretty much set. So like all of your state in Ethereum is stored in one big Merkle tree, but you have no control over like how this Merkle tree is structured or where like what data is next to what other data, which means that Ethereum effectively has to assume that your data is kind of all over the place and charge you gas onto that assumption. In Filecoin, if you have data that is frequently accessed or like frequently accessed together, you can put that data next to each other, at least in the built-in actors or in these actors. And that means that like when you read this data or if you're modifying it together, it can be less expensive because the system can sort of fetch it as in bulk as a batch. So it's a little more flexible. Yeah. On the other hand, you have to think a little bit more. Yeah, and finally, network transparent access with IPFS. Again, IPFS is built in IPLD. IPFS is a bunch of transports for sending around IPLD data. The really cool thing about this is it means that you can fetch Filecoin state, like state tree state, over IPFS protocols. And we even have IPFS implementations in the browser. So this is really cool for light clients, because it means you can build a light client in the browser They just like effectively is built on IPFS technology to fetch bits of the Filecoin state tree. And also because this comes to the next section, because we're building everything in WASM, you can then run the Filecoin smart contracts in your browser without having to run like an entire like EVM in JavaScript or anything like that. You can literally like just like use the built-in WASM VM to run the smart contracts. So like, the idea here is you get really good light client support and good support for browsers. Now, in terms of like how much of this has already been built out, not much. One of my colleagues, Adine, has actually built some demos around like FVM clients in the browser, but this hasn't like we have not had enough time or like resources to actually like explore this fully. If any of you want to play around with this, I'm sorry, this is cutting it out a little bit. I highly recommend it, or highly recommend trying to like buid light clients in the browser. It would be a fun project. Not easy, but it should be fun. Sorry, I'm trying to make sure you can hear me. Okay. Next point is on WebAssembly. So again, we built the FVM on IPLD. All of our state trees are stored in IPLD. If you call from actor to actor, we send IPLD blocks around. That's how that all works. The FVM is also again built on WebAssembly. We did this because you get basically near native performance. One of the really cool things about WebAssembly is that like WebAssembly VMs basically take WebAssembly and they compile it down to like your native architecture's instruction set. So it's really, really fast. It also enables static analysis and audits. So if you've ever like played around with EVM bytecode, like technically you can like jump into the middle of a data section in your EVM bytecode, and as long as like there's a special marker, effectively just like the right bytes there, you can do this. You can just jump into random data, and this makes it very hard to like analyze what could some EVM smart contract do and what can't it do. In WebAssembly, everything is very structured. Like the programs are effectively a Lisp compiled to binary format, so you can very easily tell like what can happen, what can't happen. You can see which system calls, we call them system calls. They're called like opcodes or precompiles in other systems are invoked. You can see what the actor does, what it doesn't do. So this is really cool for smart contracts. And finally, again, first class browser support. Okay, we're working through this. Finally, the FVM was actually designed to be a hypervisor. So we really wanted to make it possible to run other smart contract systems and just other runtimes in general on top of the FVM, so that users could port their existing systems from elsewhere. Like this is one of the reasons why we picked WASM, WebAssembly, because it means we can basically take other runtimes, and if you already written in Rust, we can just compile them directly, or we can rewrite them in Rust or C or whatever and compile them to WebAssembly. We also defined an entire user-defined addressing system, or created a user-defined addressing system, which is, in my opinion, quite cool. I'm a bit biased on that though. This system basically lets you have a smart contract that can manage an entire address space within the FVM. So in Ethereum, you can do this, where like if you use the create2 opcode, you can create a smart contract and derive its address from your address and the init code and stuff like that. However, like you're somewhat restricted on how you can do this. You have to the system will basically hash everything together and give you a new address. You can't actually choose the precise address. You can just choose how to derive it somewhat. In Filecoin, or at least with the F4 address class, the one we're using for our EVM, a so-called address manager actor, it's a special type of actor, can basically assign arbitrary addresses as long as they start with a specific prefix. So like for the EVM, any address that starts with F410F is managed by the actor with ID 10, which is the Ethereum address manager. This is getting a bit complicated, but the idea there is that actor can just arbitrarily assign addresses to whatever actor, or to actors on creation, which means like you can like basically address actors by email address if you want to, or anything you want. All you have to do is basically deploy one of these address managers that would somehow validate that the email is supposed to be assigned, it's like the email address is supposed to be assigned to the actor, but you can in theory do that maybe with passkeys or something like that. Now, caveat: this feature is currently restricted to the EVM or to FVM, because we're still playing around with some ideas here, and we want to make sure we don't open it up to everyone before we're ready. But if you have any ideas and any types of address classes you might want to deploy in the Filecoin network, I highly recommend that you start something called a FIP discussion. I will talk about how to contribute to the FIP discussion later, but that's basically how people propose improvements to the network. So FIP stands for Filecoin Improvement Proposal. So please make a proposal later if you have some idea of like how you might want to use like a custom address. I'm also happy to like talk about the details of how this actually works later. Because I know I'm just talking about it now. I'm not giving you concrete examples. I was trying to keep this somewhat more high level. And finally, what we would like to have is user-defined account types, so account abstraction. We don't currently have a concrete proposal for this. We have several that we've attempted in the past, but account abstraction is a hard problem. And we really want to, if possible, bake this into the protocol and not have to rely on third parties because we feel that's a better user experience. And we have several proposals here, but it's all complicated, so we're still working on that one. But yeah, okay. Now that I've covered why the FVM in quite a bit more time than I thought it would take, we're going to go through a Filecoin speedrun. This part should actually be a little more approachable, and it's going to cover basically like how Filecoin works at a very high level from the blockchain perspective. I'm not going to talk about how data is stored or anything like that. This is just like how messages land on chain, get executed, this kind of stuff. It's the same stuff you would run into in Ethereum with how like transactions land on chain, stuff like that. Okay, so messages are all from an account to any account or smart contract. They're signed by the account's public key, the same as in Ethereum. A message or a chain message or tuple message is the same as a transaction in Ethereum. Every message has an incrementing nonce, again, same as in Ethereum, where like you require the chain will execute basically like the message with nonce 0, the nonce 1, the nonce 2, all from the same account to ensure that you can sort of like stack up messages and send them all in sequence, and then they'll all be executed in that order you specify. And that's the sort of the actual definition of the message. It's a bunch of stuff there we don't really care about too much, but yeah, it's just a bunch of fields. Okay, so how this works is first the user, they create their message, they sign it, then they broadcast it to the network over PubSub using libp2p. So Filecoin uses libp2p. You can also use libp2p. It's a general purpose peer-to-peer networking system or library. And it also has a pretty good PubSub network, like your PubSub library built into it, that you can use to broadcast things like messages or blocks or whatever on a specific topic. So this is how we tell everyone, hey, I have this message, please include it on chain. And if you are interested in this, you should watch the libp2p talk in pod 3, and I believe it's at 5 p.m. But actually, you should check the latest version schedule because that has all been changing and probably has changed since I wrote these slides. Okay, so now that we've broadcasted out our message, someone's going to need to include the message. What happens here is that storage providers, these are effectively our miners or our block producers, will receive receiver, okay, spelling, okay, sorry about that, receive messages from the network of our PubSub and sort of collect them locally. And then every 30 seconds, some set of these storage providers are elected to mint blocks, and they pack these messages into blocks and publish them to the network. The one interesting thing about Filecoin is we have something called expected consensus. So we actually don't have one winner at every epoch. We have expected 5. So every 30 seconds, we expect 5 storage fighters to win a block and mint a block. However, this is probabilistic, so it can be anywhere from 0 to like 15. It probably won't be 15 very often, but it can be some number. We did it this way because it means that this was the sort of the simplest way to build a single round consensus protocol where no one can know who won like the election before they announce to everyone, basically announce the blocks. Many of the single leader election protocols, the non-expected consensus, the single leader ones that sort of elect a single block producer, either require lots of rounds and complicated logic, or they basically let everyone know who's going to win beforehand, and this could cause problems like denial of service attacks and stuff like that. That gets into, it's not too important for now though. Yes. So they are selected based on their power. So basically, so the details here are like they have to run some computation over the storage. It's part of proving that they have the storage. Based on that, and then based on the private key, they make a random number basically, and then if the random number is less than some value based on their power, they win the election. And then we've tuned all the probabilities here to make it so that we expect 5 winners. So it's a lot of math. Yes. Yeah. Well, so this is, Yes, yeah, it's proof of space-time. Yeah. Exactly. Yes. Yeah. So this is basically the point of the Filecoin network, where we wanted storage providers to have power in the network proportional to the amount of data they're storing. So it's not just like proof of stake. You can't just like put down tokens and get power from that. You're not just like cracking hashes on a GPU or anything like that. Instead, you have to actually store data and then continuously prove that you're storing it. And it's also not just random data. You're actually storing like user data in many cases. So it's not just like the network doesn't just tell you, oh, store this random data. You actually like you take user data, you run this some very complicated process called sealing. I'm not going to get into those details, focusing on the blockchain side of things. But yes, basically storage providers are storing user data, and based on the amount of data they're storing, they get more and more power in the network, and they win more blocks and get more block reward and all that fun stuff. Okay. Yeah, so the winners, again, they pack the messages in blocks and then announce the blocks over PubSub the same way users announce messages. They announce it over a different topic, over the block propagation topic, not over the message propagation topic. But that's how they tell everyone, hey, I won this block. Please build your chain on this block. Mike?
Can you tell me something more about PubSub?
So PubSub, it's based on Goss. Well, it's a gossip sub network. That's not going to help you. It's a publish subscribe network. So basically, the way PubSub works, or the way PubSub protocols work in general, is everyone who's interested in some topic subscribes to that topic. Anyone who has a message for that topic publishes a message on the topic. Then everyone who's subscribed gets the message. So it's kind of like a chat room where like everyone just sort of joins the chat room. You post a message in the chat room, everyone gets it. But it's a chat room for computers. So that's how we distribute things in the Filecoin network. Now, there are a bunch of features here to make this more secure, because it's kind of an open chat room, so people could spam it or cause problems. So then we have basically like a large part of Gossip Sub, our implementation of this, is around like keeping track of peer reputation. So we're keeping track of like, hey, this peer has given us useful information or bad information, or like information that you should have known was bad. And if they're giving us bad information, then we sort of like stop receiving their messages, maybe eventually just disconnect them and go away. If they're giving us good information, then we keep on propagating that. So that's how PubSub. That's what PubSub is. It's basically just one big chat, it's many chat rooms with different topics for computers.
And PubSub maintains the state of the FVM.
No, it does not. No, it's just for propagation of messages. It's just a chat. It literally just broadcasts messages to nodes on the network. So the nodes themselves maintain the state independently. PubSub is just a way of shouting out, I have this message. Everyone, like it's completely ephemeral.
So it shouts the message to the nodes.
Yeah, it just shouts the message to the node. That's it. Yeah, it's just a broadcast system. It's a more efficient broadcast system. So we don't just contact everyone and send it to everyone. The way Gossip Sub works is you send it to a few parties, they send it to more parties, send it to more parties. So it's like still you'll get a lot of messages the same. Or you'll get the same message many times, but not like once from every single peer in the network. But again, it doesn't like it's Gossip Sub is actually in PubSub is entirely separate. So this is a libp project we were just using inside of Filecoin. Ethereum actually uses this as well, I believe, for the beacon chain for broadcasting blocks, if I recall correctly. I can't remember what the latest status on that is, or at least some Ethereum nodes use it. I think they have multiple protocols. But yeah, so that's what PubSub is. Okay, and again, you should definitely go to libp talk. They'll be talking about this. Tip sets. Okay. Remember how I talked about how we have this thing called expected consensus? So expected consensus produces multiple blocks at every single epoch, at every round. So every 30 seconds, we get like on expectation 5 blocks. Instead of just throwing away most of these blocks, we actually keep them all. So when you produce a block, you don't just, first of all, like when you receive blocks in the network, you receive all of the blocks from that round, and sort of you form these things called tip sets from the blocks you receive. It's literally just a set of blocks. It's the set of tips or of chain heads that you have. But then when you create a new block, you actually point at a parent tip set. You don't point at a parent block. So like in many blockchains, every single block has exactly one parent. In Filecoin, every single block has a tip set of parents, has a bunch of parents. The one constraint here is that your parents in a block must all have the same state and must also point to the same parent tip set. So grandparent tip set in this case. So basically, for every block, the grandparent tip set is always like the same for every block in the parent tip set. So like every single one of these blocks here will point to the exact same set of blocks in the parent. But what this means, we kind of have is a continuous braid of blocks moving along.
And these 5 blocks are those that the 5 miners produce.
Yes. Yeah.
So, so the miners are 5 miners were asked to produce the next
Yep.
block, and so is there a guarantee that all the 5 blocks that would be produced by the miner would they be same?
No, there's no guarantee they'll be the same. There's no guarantee that anyone will actually see them all. So what can happen is like people's blocks will be missed. They'll be published, but not like someone won't pick it up fast enough. There are incentives on the networks to pick up blocks because like the more blocks you pick up, the more power your block has. But there's no guarantee. There's actually no guarantee that a block will be produced at a round or at an epoch. You can have 0 blocks. We call this a null block round or null round.
Okay, so then that you said na, that how you ensure that it points to the same set of block that resumes the same state.
Good point.
Yeah.
So what we do is basically we actually collect sets of tip sets. So when we receive blocks from the network, we will have sets. We will group sets of tip sets. Or sorry, we will group. Sorry, that's not the correct way. We will group blocks into tip sets based on their parent tip sets. So we'll actually end up with multiple. We'll have sets, a set of tip sets at every single round, and then we will pick the heaviest tip set. So the heaviest tip set is effectively we look at like we have a power function where we look at the basically the amount of storage onboarded in the block, the height of the block, the amount of storage lost, a bunch of like stuff like that to try to pick sort of like the best tip set. I think we also look at the number of blocks in it, and that's how we find like the one we're going to build our next block on top of. But yeah, it's so I was technically incorrect in the previous slide. We don't just get one tip set; we actually get many tip sets at each, or sorry, potentially many tip sets. Usually it's one, but if there's any forkiness in the network, any problems, you'll get like one tip set and maybe a couple of random blocks that are in that tip set. Usually you do have like a sort of a bigger tip set you can pick. So yeah, this is how tip sets work. Okay, now we can finally start talking about the FVM. So the FVM handles execution. So remember when I said that you take your block, you put the message in, you broadcast to the network. So when you over PubSub, when you do this, you like what you're actually doing is you can't just like put messages in a block. You have to also execute messages somewhere. So what we do here is we take all the messages from the parent tip set of that block and we execute them all together. So Filecoin is a bit weird. In most blockchains, when you receive a block, you execute the message in the block. In Filecoin, we take all the messages from the parent tip set of the block and execute them all together. So it's something we call deferred execution. So when a message is included in a block, it's not executed immediately. It's executed in the next epoch when that block is included in a tip set that is a parent tip set of a block produced in the next epoch, which can lead to some confusion. Actually, lots of confusion. But it's actually like this. Yes. There are advantages and disadvantages. The main advantage of doing this is that it's slightly harder to censor the network because like on a traditional network, if you win the block, you can be pretty sure that you've won, so you get to decide what you want to include, and that's it. The cool thing here is that when you win the block, like you know that other people have won the block at the same time. So like if you think you are the best winner, which you can usually determine by looking at like your basically the power function, you can then greedily pack your block with messages you want to include. But if you think you've won, but you're probably not like the best winner, because we do actually have a ranking of winners, you're incentivized to pick other messages that other nodes would probably not include. So this makes it harder to like control what actually goes into any single epoch. It also means that like we get 5 blocks in every single epoch. So like if someone's trying to censor you, like it's just much harder, because like instead of like only one miner at every single every 30 seconds, you get 5 every 30 seconds. So it's just like you would have to like basically collude with a lot more parties to censor anyone. So I believe that was the main thrust of this. It also keeps prices down because again, like you can't like if you're minting the entire block yourself, you can try to drive the prices up. But if you can't, like if you know that other people would mint in the block with you, you try to include messages that other parties have not included, because this is actually an important thing here. When we execute these messages, we deduplicate them. So if you have like the best block, we take all the messages from the best block first, or the most winning block. Then we take the messages from the second most winning block. then the third, et cetera, et cetera. So if you're way down that list, you're incentivized to pick messages that the better blocks will not have included, because then you'll get the tips. If you include messages that are duplicated, you won't get those tips. So it's basically a bunch of mechanisms to ensure that we get some nice diversity in the messages selected in the block. It does cause a lot of frustration, though, because it does mean that when you mint a block at an epoch, when you produce a block, you don't actually know what's executed there, so it makes it very hard to do MEV. And it's also one of the reasons why implementing things like account abstraction is rather difficult. That plus deferred execution make MEV and account abstraction non-trivial. Yeah. But okay, now the important part here is when I produce this block, I both point to the parent tip set and I point to the state that was computed by the FVM from executing the messages in the parent tip set. So basically, when you produce a block, you take all the messages out of the parent tip set. You take the state from the grandparent tip set. You apply the messages to the state from the grandparent tip set using the FVM. That produces a single root CID, content ID, or like root hash of the new state tree that you then include in your current block. And the whole reason I had this entire part of the presentation was to point at this here and say, this is what we're going to talk about. But I felt that you would all need to know the rest of this to understand how the FVM fits into the system. But yeah, basically the FVM is just this. It does not handle block propagation. It does not handle like message propagation or any of that stuff or consensus. All it does is execute messages and basically take a previous tip set, take a bunch of messages, apply or execute those messages on that tip set, or sorry, on that state root, and then it gives you back a new state root or new state tree. The state tree is, again, it's a Merkle tree. It's the same as in Ethereum, where like they have it's Merkle Patricia trie. We have a similar thing, except for it's an IPLD-based state tree. Okay. Now we can talk about how the FVM works. If you're still with me, I hope. Sorry. Okay. The FVM. This, I hope, is not too scary. So this is kind of like the overview of all of the different components, and I'll be referring back to this quite frequently. But this is getting to the part of the presentation where it's like, this is very useful if you want to contribute to the FVM, or if you really want to know how it works, but it's going to get a bit technical. So yeah, I'm not going to describe it yet. I'm just going to start walking through it. Okay, so actually, I will describe part of this. First of all, at the top there, you see this thing called the executor. The executor is the component of the FVM that takes messages and executes them. It's the part that actually applies the messages. The machine, this part right here, is basically, it represents the state of the system or the state of the machine, and the executor applies messages to the machine. So that's the general model you should think of when you think of the FVM, where you have this component that basically is taking chain messages. This is why I introduced the distinction between chain messages and all the other messages. The executor takes chain messages and applies them to the machine. The way it does this is it uses a bunch of other components that are in here. Next up, I'm going to start walking through this. We start out with a message coming from we start out saying, okay, we have a parent state. We're trying to like compute some state for my new block that I'm producing. I have a bunch of messages from this parent tip set, and I have the state from the parent tip set, and I want to apply the messages to that state to get my new state. To do this, I need to construct an instance of the FVM. Every single time we have a new epoch, we construct an entirely new instance of the FVM to sort of ratchet the system forward and move to a new state. To do this, first of all, we construct an engine for the FVM. The engine is something that actually lives across epochs or between blocks. It basically represents the current configuration of the network. Occasionally, we will have network upgrades, at which point we will create a new engine to represent the new configuration. So this is like the gas rules, which WASM instructions we allow, that kind of stuff. But this kind of lives more like across time, and this is where we cache a lot of the stuff it's not like doesn't change every single epoch. But then we actually execute the tip set. We construct the machine again from the parent state, and we construct an executor to execute messages on this machine. And again, I repeated this diagram many times. Again, so we have the executor that we construct every epoch, and we use that to apply messages to the machine. Okay, now how do we do this? Again, every message has a from, a to, a value, a method number, and some parameters, and other fields we don't care about here. But these are the important fields. From is the actor or account sometimes that is sending the message. To is obviously the receiver. The method number, as I was talking about earlier, it's equivalent to Solidity's API function selector. And the parameters are not actually raw bytes. So in Ethereum, parameters are raw bytes. In Filecoin, parameters are IPLD blocks. And this is important because in Ethereum, okay, technically they're raw bytes. Usually they're Solidity encoded, but the Solidity encoded bytes don't actually tell you anything about the structure. Or Solidity API encoded bytes don't like. There's nothing in there that describes the structure of the data. I cannot look at a call in Ethereum, like basically, unless I already know the signature of the function you're invoking in Ethereum, I cannot know how to parse that information, that data. I need to basically have a massive table that maps function selectors to like function signatures, so I can actually decode your parameters. In Filecoin, our parameters are encoded with IPLD, which is it's something called self-describing. So like the data itself has internal structure that you can decode without any additional extra information. Okay, I need to speed up a bit. Okay, so chain message. Yeah, again, I was talking before, different between message and chain message. Chain message is a message that's directly included on the chain from an account to, or from an account, not necessarily an arbitrary actor, and then to any Filecoin address, and again, executed by the executor. Okay, I don't issue that. Okay, actor invocation. So this is getting into the weeds of how the FVM really works under the covers. If you remember this diagram here, I've shown you many times. Basically, to invoke, so actors are WASM modules or WebAssembly modules. They're Rust, usually in our case, Rust programs that are compiled to WebAssembly, and they export a single function. The single function is invoke. So you can't call other WebAssembly functions on an actor. You call invoke, and when you call invoke, you pass in a parameter block handle. Think of it kind of like a file descriptor that refers to a like this refers to an IPLD block, and it returns a block handle that refers to your IPLD block return value. So everything in the FVM is again built around IPLD blocks. So when I say like one actor sends a message to another actor, what I mean is one actor sends an IPLD block to another actor, and the way this works is through these block handles that are again like file descriptors. I'm going to get into how this works in a second. If you're into WASM, you'll notice that this is WAST or WAT actually. It's WebAssembly WAST or WAT. I actually can't remember which one it was. But whatever. It's I think it's actually WAT. It's basically WASM assembler. And this is like the literal definition of an invoke or the invoke method for a Filecoin actor. You export an invoke function that takes one I32 in and returns an I32. Yep. Yep. Yeah. So this is like that, but this is at the FVM layer. Later, I'm going to get into to explaining how we do this at the EVM layer. And I know I'm late for his talk. I will try to speed through this a little faster. Okay. Yeah. So basically, that's this invoke here. You see that invoke? That's what I'm talking about. Where when we execute a message on the machine, the executor actually creates this thing called the call manager. This manages the call stack of actors. So like it's like a stack on a normal CPU. So we have this call manager that manages the call stack. The call manager will invoke the first actor. This actor will then run some WASM, and they can actually call back into the system or into the FVM via something we call a syscall. It's from a WASM perspective, it's called the host function, and that calls is something we call kernel, which basically like it's all the state that's relevant to that actor. And then if you want to call another actor, the kernel can call back into the call manager, which can create a new kernel, which can create a new invocation container, and sort of go all the way down recursively. But now I'm going to take a little bit of a side because I'm assuming you were all a bit confused when I started talking about these block handles, because like what are these numbers doing here? So I'm going to take a bit of a side and talk about IPLD again because I keep on talking about IPLD. The way we work with IPLD in the FVM is kind of the same way you would work, or similar to how you'd work with files in a file system, where first you take a CID and you open it, same way you open up a file. A CID is again a content ID or content identifier. It refers to an IPLD block. Actually, I realize I'm saying block many times. IPLD blocks and Filecoin blocks are completely different things. IPLD blocks are content address bits of data. Filecoin blocks are blockchain blocks. Unfortunately, they use the same words. So this gives you back a handle. Handle just a number. You can then read the data from that handle. You can also create a new IPLD block by passing in the multi-codec. Multi-codec is, remember when I was talking about CIDs and I said there are 3 pieces to it? There was something called a codec that describes the type of data you have, another magic number that tells you the type of hash, and then the hash digest. This is that first magic number. It's the one that tells you what type of data you have. So this multi-codec, in the case of Filecoin, usually it says you have CBOR data, or concise binary object representation. It's a standardized format. And then, so when you create an object, you say, here's some data, and here's the multi-codec. Here's the encoding of the data, and the system will give you back a handle, and then you can call link, and with the hash function you want to use, and this will basically take that data you've written, hash it, and give you back a CID. So this is kind of the entire life cycle, where you can go from CID, read some data in, mutate it, and then go back to a CID. So this is the whole life cycle of reading state and parameters and everything in the FVM. Tomorrow, I will talk about how CIDs work in more depth and how IPFS works. So if you are interested in any of this stuff, please come to that talk. It will actually be a lot more approachable than this talk. I'm sorry, this talk is very low level. Okay, syscalls. So now we just talked about, you've seen these. These are just random function signatures that doesn't really tell you what they are. The way we implement this in the FVM is through something called a WASM host call. I don't know how familiar, actually, I should be asking this. Who here is familiar with WASM and host calls in WASM? No one. Okay, I really should have asked that earlier. Okay, so WebAssembly has this method for calling out of the WebAssembly module, where your WebAssembly module is running this VM, and you can call into the system via something called a host call. The way this works is you basically, you declare to the system, I need to import some function, and then you run a special operation, in a special instruction inside your WebAssembly module that tells the system, hey, I want to call this external function. Here are my parameters, etc., and here's the name of the function. Then the system can then call a function like in your host, so like in the browser, or in our case, inside the FVM, to perform some functionality that cannot be performed inside your actor. So these here are all host calls, because the data, your Filecoin state tree, or the state of your Filecoin actor is not stored inside your actor. It's stored inside your client that is validating the network. So this is how we get data in and out of the system. It's somewhat like in the EVM, you have like sload and store and stuff like that. This is our equivalent to sload and store. And we implement it through host calls. I'm actually going to skip this part because honestly, this is like really, really in depth. If you want to talk later about like how this works, I'm around, but it gets really confusing. So I'm going to skip that. Okay. Next up, I've talked about how to create IPLD blocks, but I haven't actually talked about how do you actually modify your state. So one final bit we have is this ability to set your state root and get your state root. So basically, every single actor in Filecoin has its own completely independent state root. So it's not like Ethereum, where in Ethereum, you have one big Merkle precision trie that stores all of the state, and everything's kind of mixed together. In Filecoin, you do have one big state tree, but then every actor has its own separate state tree hanging off the leaves of that big state tree. So basically, you have one state tree that references all the actors in the system, and then separate state trees per actor. The cool thing about this means that you can snapshot your state. So if you need to snapshot and roll back your state, you can literally just get your state root, put that in some other object, and then store that object, and basically go through this process to create a block that references your previous state, and then store that new object. Which means and we actually use this on Filecoin, where we have certain things where we need to snapshot the state because it might need to be disputed later. And in something like the EVM, you need to copy a bunch of state to make this work. In our case, we can literally say, okay, let's stash a copy of our current state for now and keep on mutating it, and then later we can delete it if we find out we don't need it. So it's just really, really convenient. It's, if you've ever worked with copy on write file systems, it's the same kind of idea. Okay. Finally, to send data or to call between actors, we use this send functionality where we send a message. Yes. Yes. So no, an actor is it's a smart contract basically. So we call them actors because we're following the actor model. It's a programming model, but it's smart contract. It's not. So it depends on what you mean by node. Node is very heavily overloaded. What's node? Sorry, what for you? What do you mean by node? Yes, I see. An actor is not a guest node. Yeah, so a guest node would be a validator or a client. An actor is more like a smart contract or an account. Yeah. So these actors are then put in this one big state tree, and like they are the unit of code on the network, not the unit of validators, I guess, of like machine. Okay. Again, for calling other actors, we send messages. This same as was discussing before, we send IPLD blocks from actor to actor. I'm not going to get too much of the details here, but it's like we've already covered this. Yeah, okay. So the FVM also has support for events. I won't get too much of the details, but basically, so in Ethereum, you have events where you have like 0 through 4 keys and then a value. In the FVM, events are just key value, key value, key value, where the values are actually structured. So you can have arbitrary, again, IPLD structured data as your event value, which means like it's not just bytes. And then your keys are always UTF-8 strings, or sorry, Unicode strings. And basically, the design is trying to mimic structured logging. So if you ever use a structured logging library, we can basically just like log a bunch of key value pairs. That's exactly what we're trying to do here, because it's significantly more general than something like Ethereum, where if you want to add more data to your event, you have only so much space to really add it. This lets you just sort of keep on expanding your event. Yeah, so that's the idea. However, we were able to then map Ethereum events onto this format. So that's why we took this format, because it's a more generalized way of emitting events. Okay, what is FVM? I'm going to start going faster now. FVM brings the Ethereum ecosystem to Filecoin. That was the entire point. Where we built Filecoin, we built the FVM, but we didn't have support for smart contracts. And we realized that, okay, we could try to like rebuild the entire Ethereum ecosystem with like smart contract tooling and all of this stuff, but that's hard. So instead, we decided to just add support for it in Filecoin, where we built the EVM, or an EVM interpreter to run inside of the FVM. We implemented the Ethereum JSON RPC API inside Lotus, the sort of one of the main clients that we have on the network, equivalent to Geth. And implemented some features like actually just like send regular Ethereum messages on the Filecoin network, and it just kind of works. There are a lot of edge cases because we are not Ethereum, we are Filecoin, but most of the Ethereum tooling should mostly work. One of the big caveats here is that the gas numbers will be completely different because gas on Filecoin is much finer grained. The ratio is like it's off by like 3 orders of magnitude. So like basically you will see very large net gas numbers in Filecoin. That doesn't mean that something is necessarily really expensive. It's finer grained gas. Yeah, and then we implemented events of the FVM event system. Okay, so one thing we really wanted in our implementation of the EVM is we didn't want to have like the EVM be its own special thing in its own little corner. So a lot of systems that have implemented EVM support, they implement basically the entire EVM in one box and put it off in its corner, and EVM actors talk to EVM smart contracts talk to EVM smart contracts, and the rest of the system does its own thing. We didn't want to do that. We wanted everything to be part of one big system, so that like everything was a first-class citizen. So that's why we have the EVM interpreter compiled down to a WebAssembly smart or actor in our system, so that like every single EVM smart contract is a separate Filecoin smart contract and a separate Filecoin actor. Has its own top-level Filecoin address, and can be interacted with using all of the normal Filecoin tooling as well, and can also interact with all of the Filecoin tooling. Mostly, there's some caveats, but like you can write an EVM smart contract and send a message to a storage provider's actor on the network, or a minor actor, as it's called. You can send a message to the storage market. You can make storage deals and do all that kind of stuff from an Ethereum smart contract without having to go any through weird proxies or anything like that. You just call it directly. Yeah. So we also wanted to avoid having too much special classing and special support just for the EVM, because again, we want to be this what I call hypervisor. We want to allow sort of or we want to support arbitrary smart contract ecosystems and VMs without necessarily just special casing one or two of them. We did have to add some special cases for the EVM. We're hoping to eventually get rid of these and generalize them. So, for example, like right now, we don't have proper account abstraction. We kind of have like a fake version that just works for Ethereum for Ethereum wallets, and that's it. Eventually, we want to open it up so like you can sort of like make whatever type of wallet you want and just works with Filecoin. Unfortunately, we don't quite have support for that. Okay. But again, yeah, everything works with Ethereum tooling. You can use MetaMask and Filecoin. This is why you can use MetaMask and Filecoin, even though we're not Ethereum. Like if you look at the actual technology of Filecoin, it looks nothing like Ethereum. But it just kind of works with Ethereum tooling because we've been putting all these translation layers and mappings and everything. Okay, how FVM works. We don't really need to go over this. This gets really, really in depth. But basically, effectively, like we have EVM compiled into WebAssembly, and then it uses native FVM, like the native FVM to call between actors. And we also have a mapping of EVM events to FVM events. Basically, how we map keys, or we map the keys and the values from EVM to FVM, which is this more structured logging like, and this is EVM tuple. And now questions, if you can still remember anything I talked about. I will post the slides online.
What are problems people have like taking a regular contract on like Polygon to FVM or something like that?
Can you?
Yeah, like what are common issues like people have from taking a traditional EVM contract and moving it to FVM?
So there are various problems. Usually it's some minor JSON RPC or like API incompatibility. We did have like one bug in the EVM implementation, but that was actually only a problem for like one user. We also have some problems with like, let me think, like, what was that? Someone had, we don't support legacy transactions. Yeah, so we had some people who were trying to use like, I can't remember what it's called, but like effectively you can sign a message and send it to any chain. We don't actually support that. If you have to sign a message for the Filecoin chain, because you have to use the new transaction type that specifies the chain ID. But this meant that like if you're trying to like deploy the same smart contract on the same address on different networks, it was difficult to do that. So that was another problem people ran into. Let me think. Some of like when you start interacting with the native smart contracts, things can get a bit weird because like it's a different calling convention. So like native smart contract, for native actors, we send IPLD blocks around as our way of calling each other. And in the EVM, you have Solidity encoded or Solidity ABI encoded data. So they're completely different formats. So we had to write some libraries, or actually hired some people to write some libraries that translate between the two. But this can get a bit complicated and difficult to use. Yeah, but you can use so these are some of the problems we have. I don't know, like sometimes our RPC providers will have issues. Where like right now, apparently they were having some issues like estimating gas for some of our users. And that is always very frustrating because then like if you use like the default estimated gas by like Remix, it'll be totally wrong because again our gas units are much more fine grained. So you basically need to multiply the default gas by like 300 in order to get a gas value that actually works. So this has been a problem. Yeah. Actually another problem people run into is we have 30-second block times, which people coming from Ethereum really don't like for a good reason. We don't have the Ethereum beacon chain, so we don't have the same kind of finality. We're still based on longest chain finality, which can take quite a while. The safe number is 900 epochs, or like many hours. I think it's like 8 hours or something, 8 hours and change. That's absurd. Most people just wait like a half an hour, but still that's a long time when like in Ethereum it's like 6 minutes and you're finalized. Another issue people run into is our deferred execution. So because we have 30-second block times and we also don't execute a message for another 30 seconds, this means it basically takes a minute to get a message executed. While we actually have throughput, so we can execute quite a few messages. it's like there's a high latency where like you send a message and it takes a long time for it to actually like get executed, even if it's picked up in the very next block. So this is another problem people run into.
Filecoin Saturn is a content delivery network. Do we have any standardized templates as such for content management?
For what? For the FVM?
Yeah.
So the FVM is not about transferring data. It's about like managing chain state and like running smart contracts.
No. Actually, even the standardized way of.
No. So on chain, no, because basically the only chain state you can access on chain is your actor state. We actually have a bunch of logic for ensuring you can only access that state, because like we cannot guarantee that everyone on the network has all of the state stored, like all of the Filecoin sectors, because that's like a lot of data, and no one can store that. Well, some parties could store that, but no one who's on our network would be able to store all that data.
Okay. Thank you.
Yeah. So like there are people who have worked on. I don't know what the current status of this is. Matt can answer more around. Basically, what we end up having to do here is kind of like a data marketplace, I guess, or effectively like you would send a message to some market or some bounty system, and then your storage provider who's storing your data would have to then like fulfill the request that you've made and have to give you the data. So you could have something like that where basically you could ask your storage provider to put the data on chain, and then you could use it that way. Other ways of doing this is with IPC, where like with IPC, you could create a subnet that also runs on the FVM, where all the storage providers on that subnet would basically be storing your data. It would all agree to store all the same data, and that subnet would actually be able to give access to its data to the smart contracts, and that's something I really want to see. But we can't do that on the Filecoin mainnet because it would mean that everyone has to store everything. So like, for example, like Arweave could do this because Arweave, everyone's, well, actually, no, they couldn't because they don't even guarantee everyone store everything. Yeah, it doesn't scale. That's the problem. Right. So for Filecoin, we have mainnet and we have calibration net. And people will spin up other small networks. So like you could spin up your own DevNet on your laptop pretty easily. And there's some Docker containers that will make this really easy to do. We also will occasionally spin up something we call Butterfly Net for just like testing things. But that's mostly for internal stuff. The one you want to use is Calibration Net.
Hi. What are some possible applications? Hi. Here.
That's it. There you
go. What are some possible applications for FVM?
Well, so anything you might want to do with a smart contract. Sorry, that was very fast. Anything you might want to do with a smart contract. Additionally, like one of the reasons we added support for smart contracts to Filecoin is that we want people to be able to write things like data wallets. So the concept of data wallet is like I want to be able to like put basically have some data stored on Filecoin, and then have some smart contract on chain that is responsible for ensuring that my data doesn't disappear. This is also related to this thing we call data DAOs, or data decentralized organizations, or decentralized autonomous organizations. It's the idea where like you have a smart contract that can manage some set of data and basically pay for its continual storage, even if the owner or controller walks away, or even if there is no controller. So these are the kinds of things I really want to see. The other thing we can do is like, one second, like right now the current market that you can use to sort of make storage deals is inefficient and not very flexible. We would like people to deploy alternative marketplaces for basically making data or storage deals and play around with that, and it's just not possible without some kind of on-chain state. This also really enabled like things like lending systems and stuff like that, where like you can have like I can have a smart contract own a storage provider, and that yields really interesting structures because then I can have a group ownership of storage providers, and that's something that was impossible otherwise.
So my question was more on the lines of, let's say there's a data DAO who owns some data. Mm-hmm. Can we do some kind of computation on top of that? Like let's say a machine learning model which runs inference on top of that data DAO's data.
You could. The main file blockchain would not do this inference for you because that would be really expensive. What you could do, you have two options there. Either from the main Filecoin send a message to some cutting it out. You would send a message to some other site and the site, or like some smart contract, and then that smart contract would signal some external system to go perform the computation for you. One of the cool things is because you're storing your data on Filecoin, like they would immediately know, oh, go to this storage provider to fetch the data, and like so like that all the information is available. Another way of doing this is again with IPC, where like I would like to see IPC subnets where you have all of the basically the participants on a single subnet, so basically all perform the same computation, so you can sort of like make sure they're doing it correctly. And then you send a message to that subnet. That subnet would perform your computation, your inference, or whatever for you, and then return your answer to the mainnet. Honestly, a lot of these compute-heavy use cases will probably involve, again, IPC or subnets, because like there's only so much bandwidth we have on the L1 chain. But also, I mean, IPC uses the FVM, so it's still the FVM. It's just not on Filecoin mainnet.
There's also a project called Lilypad, and there'll be a workshop tomorrow on Lilypad, which is a connection between FVM and big web AI.
Yeah, so that's using like basically just a decentralized compute network where effectively you send a message to a smart contract, and then that gets the job scheduled for you, and then the result will be returned to the chain, all that kind of stuff. There's no guarantee it'll actually work because basically everything on Filecoin has a lot of guarantees because like basically everyone is forced to perform these computations. In a system like this, like they could just drop your request. It's like the internet, but you can use this, and there are a lot of ways of aligning incentives and paying for operations and that kind of stuff.
Couldn't this work through like an optimistic system where you just
yes, I believe that's how Lilypad works. But you should go to the talk tomorrow. Yeah, I'm not on that team. Could you pass the? Sorry.
So if we talk about the terminologies of say an L1 and an L2, there's FEVM, is it an L1 or is it an L2?
So
just in context of Filecoin.
So Filecoin is an L1. The FVM is a VM for the L1 blockchain. The FEVM is a layer 2 VM. It's not a layer 2 blockchain. It's just like it's a VM inside a VM. Yeah. So I wouldn't call it an L2. I would just call it it's just a VM. It's a runtime. We usually call it a runtime. So we say like the FVM, and then we have different runtimes on top of the FVM. We say the EVM is one of or FEVM is one of our runtimes.
Yeah. And you mentioned that an FVM user could talk with an EVM user.
So an FEVM smart contract can talk to an FVM actor, like any other this is like the all the built-in actors, all of the system ones that run they basically manage the storage network. Those are all actually written directly in WASM. I also do want to note that right now users cannot deploy on Filecoin mainnet. They cannot deploy custom WebAssembly level actors because we're working on this, but there are a lot of security concerns we have there around making that tightened down and secure and efficient at the same time. So right now, the only thing users can deploy are EVM smart contracts. If you use IPC, though, you can create your own subchain or your own sidechain with your own custom set of WebAssembly actors.
So theoretically, you could have multiple chains and access the liquidity of those sort of bundles.
So that doesn't actually rely on the FEVM or the FVM. That's mostly something like IPC. That gives you the whole multiple chains working together. The FEVM and the FVM are more around having different runtimes or different smart contract systems all working together in the same system. And I am not keeping track of time.
How do you see the FEVM playing out as a L1 EVM ecosystem versus the use cases that you want to see? Are you seeing a lot of forks? Are you seeing people building these novel data and storage use cases?
What do you you mean? Sorry, what type of fork?
This the sushis and the unis and every time a new L1 comes out that's EVM compatible, there's a lot of copycats. So I kind of want to understand the current ecosystem as it is, and if it's what projects you mentioned Lilypad and things like that.
Well, so FVM again isn't really an L1. It's just it's adding EVM support to Filecoin. Filecoin is already the L1. there are many other decentralized storage networks that people have been trying to build, but that's been going for a long time. We are getting adoption of FEVM, if that's what you're asking, in terms of like people like porting the smart contracts from Ethereum to Filecoin, but I'm not entirely sure what the question is.
Maybe commenting on this. So in terms of growth and TVL, we have been leading the DeFi Llama growth leaderboard for like a couple of weeks now. So like the DeFi use case is really picking off. You should look at Glyph maybe, and then SDFill and a couple of others if you're interested in DeFi in particular. When it comes to the adoption of major protocols on Ethereum that are looking at, the Falcon ecosystem, look at the recent votes on both Uniswap and SushiSwap, who have decided to prioritize the FVM for their next integrations. So yeah, it's coming along, but it's still young. Yeah. Does that answer your question roughly?
Yeah, I also want to know like more like unique use cases to like that you want to see built kind of.
Perfect.
For that, like again, as I was saying before, data wallets, data DAOs, that kind of stuff. I really want to see that. Like I want to see systems where people can just like collaboratively choose to store, like permanently store data, and not have to like sort of like manually manage this off chain. We can have systems on chain that basically like ensure that the data never dies. There are a lot of important data sets that we have. We're lucky people are continuously storing them, but like if someone like we could get in a situation where like everyone thinks someone else is storing it and then no one's actually storing it. We don't want that to happen. So like I really want to see smart contracts on the Filecoin network to basically ensure that certain data sets stay alive.
And also, if you want to like brainstorm use cases on FVM, there's this founder track that we do in one of the other rooms. We are going to do a session on use cases for FVM and like building billion-dollar businesses on the PLN stack tomorrow. Yeah, so find me and my team there.